Welcome back, 7th grade roboticists. We are jumping right into today's explainer for Unit 2, Lesson 3, Program Flow Worked Practice. Our mission today is entirely focused on continuous sensor-based behavior. We're going to take those basic movements you've already mastered and upgrade them so your robot actually reacts to the environment around it. So let's get right into it. But first, picture this. Have you ever spent time meticulously programming your robot, checking all your distances, making sure your motors are set perfectly, only to run the code and watch it instantly crash into a wall, or maybe take a nosedive straight off a table? It is literally the most frustrating thing ever. But usually, it crashes for one very simple reason. It only checked its sensors once. It looked, decided the coast was clear, and then essentially closed its eyes while driving.
To fix that, here is today's mission briefing. We're going to cover why robots need loops, making decisions with switches, and mapping the ROM flowchart. Then we'll tackle mission levels A and B, debugging sensor flow, and finish up with the ultimate robot challenge.
Section 1, Why Robots Need Loops.
Think of it kind of like checking the weather. If you look out your window at 8 a.m., see sunshine, and then never look outside again, you are going to get completely soaked when a thunderstorm rolls in at noon. The Check Once robot does exactly that. It takes a single reading, decides to move, and ignores all new information until it crashes. The Check Continuously robot, on the other hand, is like someone who keeps glancing at the sky while they walk. It constantly updates its data, sees the wall approaching, and successfully avoids it.
So, to get that continuous checking, we absolutely need a specific tool, the loop block. By definition, a loop block is a programming structure that requires a robot to repeatedly monitor sensor input rather than checking only once, enabling continuous environmental detection. If you want complex, real-world behavior from your machine, you literally demand continuous environmental detection. The loop is what keeps your robot's eyes open the entire time your program is running.
Section 2, Making Decisions with Switches.
Now we need to give your robot a brain, right? We give it the ability to make decisions using a switch block. This is essentially an if-else command that sits right inside our loop. The logic rule is super straightforward. Step 1, if the touch sensor is pressed, back up. Step 2, else, meaning otherwise, drive forward. That right there is a complete behavioral decision. The loop asks the question over and over, and the switch provides the action. Trigger the touch sensor, the robot backs away. Don't trigger it, and the robot keeps rolling forward.
Section 3, Mapping the ROM flowchart.
Okay, let's slow down for a second and map out the exact sequence for a program called ROM. Sequence 1, we hit start. Sequence 2, we immediately enter our loop, which guarantees our robot won't stop thinking. Sequence 3 is our switch, where the robot asks, is the distance less than 10 centimeters? Now, for sequence 4, we have a split path. If yes, there is an obstacle, so turn right. If no, the path is clear, so move forward. Finally, sequence 5, return to the start of the loop. It circles right back to sequence 2 and asks that distance question all over again. A fraction of a second later, checks again. This constant feedback loop is the absolute core of autonomous movement. Section 4, Mission Levels A and B. All right, let's get into the exact parameters you need to hit for today's worked practice. For level A, your input is the touch sensor being pressed or released. Your required output? A flashing green light when pressed and red when released, repeating forever. And since it says forever, you absolutely need a loop. For level B, we are swapping the sensor out. Your input is the color sensor seeing a dark line. The output? The robot must drive forward continuously and play a sound whenever it detects that line. You're definitely going to need a loop, and you'll need a switch to toggle between moving silently and playing that sound when the line shows up. Section 5, Debugging Sensor Flow.
Let's pause for a crucial system diagnostic. Code fails, it happens to all of us. When it does, commit these 3 golden rules of debugging sensor flow to memory. Rule 1, is the sensor actually connected? Physically check the wires and check the port numbers in your software. A perfectly coded robot won't work if it thinks the touch sensor is in port 1 when it's really in port 4. Rule 2, is the loop present? If your robot does its action exactly once and then goes totally dead, you forgot your loop. Rule 3, are input data values correct? Did you tell the robot to look for a distance of less than 10 centimeters, or did you accidentally type greater than 10? A single backwards math symbol ruins the whole shebang.
Section 6, The Ultimate Robot Challenge. Here we go, the final objective. The challenge?
Combine ultrasonic obstacle avoidance with a touch sensor fallback that stops the robot and plays an error sound. So what does this mean in plain English? You need a primary loop using the ultrasonic sensor to steer away from walls, exactly like our Roam flowchart. But you also need a backup plan, a second layer of logic, another switch. This way, if the ultrasonic sensor fails to see something really thin, like a chair leg, and the robot physically bumps into it, the touch sensor acts as a fallback. It must immediately override everything, stop the robot completely, and blast an error sound so you know a collision happened. You'll be continuously monitoring two different inputs at once. It's a real game changer. To wrap up today's explainer, I want to leave you with this final, thought-provoking question. If your robot hits a wall during the challenge but doesn't play the error sound, which of the 3 debugging rules should you check first? Think back to our golden rules. Is it a loop issue, a port issue, or a data value issue? Apply those diagnostic steps to your final code, get those sensors communicating inside your loops, and I guarantee your robot is going to navigate its environment like a pro. Good luck on the missions, and I will see you in the next explainer.